An essential singularity is a point at which a function behaves in a particularly wild and unpredictable manner. In complex analysis, it's a point where the function does not have a Taylor series expansion that converge to the function near that point. For example, consider the function f z equals e caret backslash frac 1 z. At z equals 0, this function has an essential singularity. As z approaches 0 from different directions in the complex plane, f z can take on wildly different values, making the behavior of f z near 0 extremely sensitive to the direction of approach. This is in contrast to other types of singularities like poles, where the function goes to infinity in a predictable way, or removable singularities, where the function can be redefined to be analytic at that point. Certainly, another classic example is the function g z equals backslash sin backslash frac 1 z. Here, as z approaches 0, the sine function oscillates infinitely often between -1 and 1. There's no limit to the values that gz can take as z gets closer to 0, which is characteristic of an essential singularity. In both examples, f z equals e caret backslash frac 1 z and gz equals backslash sin backslash frac 1 z, the functions do not simply blow up to infinity or approach a finite limit. Instead, they exhibit an infinite variety of behaviors as they approach the singularity at z equals 0. This unpredictability is what makes an essential singularity essential. These examples illustrate how functions can behave in complex and unexpected ways near these points, which is a fascinating aspect of complex analysis. A Laurent series is a representation of a complex function that is particularly useful in analyzing functions near their singularities. It's similar to a Taylor series but includes terms with negative powers, allowing it to describe behavior around points where the function isn't analytic. The Laurent series of a function f z around a point C has the form f z equals backslash sum underscore n equals backslash inft caret backslash inft a underscore n z c caret n, where a underscore n are coefficients determined by the function and its derivatives. For an essential singularity, the Laurent series has infinitely many negative power terms, those with n 0. This infinite series of negative powers is called the principal part of the Laurent series, and it's what causes the unpredictable behavior near an essential singularity. For example, the function e caret backslash frac 1 z has an essential singularity at z equals 0, and its Laurent series around 0 includes terms like z caret n for all positive integers n, contributing to its erratic behavior near the singularity. Laurent series are powerful tools in complex analysis because they allow us to study functions near their singularities and classify those singularities based on the series characteristics. To compute the Laurent series of a function f z around a singularity C, follow these steps: identify the singularity, determine if C is an isolated singularity and classify it removable, pole, or essential. Find the annulus of convergence, determine the region around C where the Laurent series will converge. This is an annulus, a ring-shaped region, where f z is analytic. Compute the coefficients. The coefficients a underscore n of the Laurent series are given by the contour integral. A underscore n equals backslash frac 1 2 backslash pi I backslash oint underscore c backslash frac f z z c caret n plus 1 dz, where c is a positively oriented simple closed contour around C within the annulus of convergence. Construct the series. Once you have the coefficients, construct the series by summing up. F z equals backslash sum underscore n equals backslash inft caret backslash inft a underscore n z c caret n. The negative powers form the principal part, and the non-negative powers form the regular part of the Laurent series. For example, to find the Laurent series for e caret backslash frac 1 z around z equals 0, you would compute each coefficient a underscore n using contour integration and then sum up all terms. Let's compute the Laurent series for f z equals backslash frac 1 z z1 around the singularity z equals 1. Identify the singularity. Z equals 1 is a pole of order 1, not an essential singularity, but we can still compute the Laurent series around it. Find the annulus of convergence. The function is analytic everywhere except at z equals 0 and z equals 1. So, the annulus of convergence is 0, z1 1. Compute the coefficients. We can split the function into partial fractions to find the coefficients more easily. F z equals backslash frac 1 z z1 equals backslash frac 1 z plus backslash frac 1 z1, the Laurent series around z equals 1, 4 backslash frac 1 z is backslash frac 1 z equals backslash frac 1 1 plus z1 equals backslash sum underscore n equals 0 caret backslash inf t z1 caret n and 4 backslash frac 1 z1. It's simply backslash frac 1 z1. Construct the series, combining both parts, we get f z equals backslash sum underscore n equals 0 caret backslash inf t z1 caret n plus backslash frac 1 z1. This is the Laurent series for f z equals backslash frac 1 z z1 around z equals 1 within the annulus 0 z1 1. To compute the Laurent series around z equals 0, we can use the fact that the exponential function has a well-known Taylor series expansion, e caret w equals backslash sum underscore n equals 0 caret backslash inf t backslash frac w caret n n. Substituting w equals backslash frac 1 z, we get e caret backslash frac 1 z equals backslash sum underscore n equals 0 caret backslash inf t backslash frac 1 n. Backslash left backslash frac 1 z backslash right caret n equals backslash sum underscore n equals 0 caret backslash inf t backslash frac 1 n z caret n. This is the Laurent series for g z equals e caret backslash frac 1 z around z equals 0. Notice that all the terms have negative powers of z, which is characteristic of an essential singularity. The series has an infinite number of terms in the principal part, negative powers, which leads to the unpredictable behavior near z equals 0. The Laurent series of e caret backslash frac 1 z near z equals 0 is e caret backslash frac 1 z equals backslash sum underscore n equals 0 caret backslash inf t backslash frac 1 n z caret n. As z approaches 0, each term in the series becomes significant because z caret n grows without bound 4 negative powers of n. This means that infinitely many terms contribute to the function's value, and the function does not approach a single value as z approaches 0. Instead, depending on the path taken towards 0 in the complex plane, e caret backslash frac 1 z can take on any complex value infinitely often, except for 0. This is why we say the behavior is wild or erratic near an essential singularity. The function oscillates between extremely large values and can be made to approach any complex number by choosing an appropriate path towards the singularity. This unpredictable behavior is a hallmark of essential singularities and distinguishes them from other types of singularities where the behavior is more predictable. The concept of an essential singularity was introduced by the French mathematician Augustin Louis Cauchy and further developed by the German mathematician Karl Weierstrass. Cauchy made significant contributions to complex analysis, and Weierstrass formalized many concepts, including the classification of singularities. Weierstrass's work in the mid-19th century on analytic functions led to a deeper understanding of singularities. He showed that any analytic function can be represented by a power series, now known as the Weierstrass factorization theorem, and classified singularities into removable poles and essential singularities based on the behavior of these series. The study of essential singularities was further advanced by other mathematicians, including Riemann and Casarati, who explored their properties and implications in complex analysis. Augustin Louis Cauchy (1789–1857) was a prolific French mathematician who made numerous contributions to mathematics, including the field of complex analysis. He was one of the first to rigorously define the concept of a complex function and its derivative, known as the Cauchy-Riemann equations. Cauchy's theorem and Cauchy's integral formula are fundamental results in complex analysis that bear his name. Karl Weierstrass (1815–1897) is often referred to as the father of modern analysis. He was a German mathematician who gave rigorous foundations to calculus and complex analysis. Weierstrass formalized the concept of convergence of series and introduced the idea of uniform continuity. His work on analytic functions led to the classification of singularities, including the definition of essential singularities. Both mathematicians' work laid the groundwork for what would become a central part of modern mathematics, influencing generations of mathematicians and shaping our understanding of complex functions and their singularities. Their legacy in mathematics is still evident today, as their theorems and definitions are fundamental to the study of complex analysis and many other areas of mathematics. The Weierstrass-Casarati theorem, also known as the Casarati-Weierstrass theorem, is a resulting complex analysis that describes the behavior of functions near essential singularities. It states that if f z is a function with an essential singularity at a point z_0, then in any neighborhood of z_0, f z takes on every complex value, with possibly one exception, infinitely often. Here's a more detailed breakdown. Essential singularity, a point z_0, is an essential singularity of f z if f z is not analytic at z_0, and the singularity is neither a pole nor removable. Neighborhood, a neighborhood of z_0 refers to an open set containing z_0. Complex values, the theorem asserts that as you approach z_0, the function f z can come arbitrarily close to any complex value. Exception, there may be one complex value that f z does not approach. This is often 0 for functions like e⁻⁻frac 1 z. Infinitely often, not only can f z approach any value, but it can do so an infinite number of times within any neighborhood of z_0. This theorem highlights the unpredictable nature of functions near essential singularities and is a key result in understanding their complex behavior. Let's apply the Weierstrass-Gasserati theorem to the function f z equals e⁻⁻frac 1 z, which we discussed earlier. The function f z equals e⁻⁻frac 1 z has an essential singularity at z=0. According to the theorem, in any neighborhood of z=0, this function takes on every complex value, with the possible exception of 0, infinitely often. For example, consider the neighborhood around z=0 defined by 0 z⁻ for some small epsilon 0. As z approaches 0 from different directions in this neighborhood, the function e⁻⁻frac 1 z can exhibit wildly different behaviors, approaching 0 along the real axis from the right, z=x, with x0 e⁻⁻frac 1 z grows without bound. Approaching 0 along the imaginary axis, z=e, with y⁻next 0 e⁻⁻frac 1 z oscillates between large positive and negative values and complex values with large magnitudes. No matter how small the neighborhood around z=0, within that area, you can find points where f z is close to any given complex number, except for 0, which it never reaches. This behavior exemplifies the theorem and shows how functions with essential singularities can behave in complex and unpredictable ways near those singularities. That was all. Goodbye.